Have you ever wondered how doctors get those incredibly detailed, perfect maps of what's going on inside you? Well, today we're going to dive into the amazing technology that makes it all possible, the CT scanner. We're going to break down how these incredible machines went from taking hours for just one blurry picture to creating these stunningly clear images of our bodies in a matter of seconds.
So this is the big question, right? This is the problem that drove the entire invention. A regular X-ray, as you probably know, is just a flat shadow. Everything inside you is just pancaked on top of everything else. So how in the world do you get a crystal clear image of just one single slice of the body with absolutely nothing overlapping?
Okay, let's get into it. The whole challenge really starts with traditional X-rays. You see, they're two-dimensional projections of a three-dimensional thing, your body. So trying to see one specific organ is like trying to understand a whole forest by looking at a single flat photograph of it. All the trees are just squashed together. And the technical term for this problem, which our source material points out, is artifacts of overlaying structures. All those shadows from different depths just get superimposed, and that creates a really cluttered, messy image that makes it incredibly tough for doctors to see any one thing clearly. This big limitation is what led to a truly brilliant idea, a huge conceptual leap. Instead of trying to make sense of that flat, messy shadow, what if you could just isolate and image a single two-dimensional cross-section? Going from a 2D shadow to a true 2D slice, that was the absolute game changer. And that brings us to this key term right here, a tomogram. It's really simple. It's just an image of a plane, or a slice, inside the body. And the T in CT, well, it stands for tomography, which is the whole process of creating these slices. It's all about seeing the body one single layer at a time. So how does it actually work? Well, the basic idea is surprisingly elegant. First, you've got this very thin, very focused X-ray beam that passes right through the body. Now, on the other side, there's a detector that measures exactly how much of that beam made it through. Then, the whole system, the X-ray source and the detector, rotates just a tiny little bit and around the patient. And you just do it again, and again, and again, repeating that whole process from hundreds of different angles. It's kind of like shining a flashlight through a foggy glass box from every possible direction to build a perfect map of whatever's inside. Okay, so here's the really crucial point. We now have hundreds, maybe thousands of these simple, one-dimensional measurements taken from all around the body. How do you possibly transform all those simple lines of data into a complex, detailed, two-dimensional picture of, say, a human brain? This is where the magic really happens. All of those individual measurements, from every single angle, they all get compiled into this thing you see here, a sinogram. Now, look at it. It just looks like a bunch of wavy lines, right? It looks nothing like a body part. But this is the secret code. Think of it like a musical score. It isn't the final song, but it has every single note you need to play it perfectly. So, how do we turn that wavy musical score into a clear image? What's really interesting here is that if you just try to layer all that raw data back together, what we call back projecting, you get a hopelessly blurry mess. It's useless. The secret is this brilliant mathematical trick called filtered back projection. It's kind of like taking a blurry photograph and applying a special filter in software that just instantly sharpens all the edges. The algorithm removes the fuzziness from the raw data before assembling the picture. And when all that newly sharpened data is put back together, the blur just cancels itself out. And what you're left with is that crystal clear slice of the body. Amazing. Now, this whole reconstruction process is brilliant for sure, but the very first scanners, they were painfully slow. So the next big challenge was speed. How do you take a process that originally took hours and make it fast enough for a busy hospital, or maybe even fast enough to scan a moving organ like a beating heart? And just look at this timeline. It's absolutely incredible. The very first clinical machines back in the early 70s took several hours just to get one slice. By the 80s, thanks to some new designs, they got that down to a few seconds. Then came helical scanners, which could capture an entire torso in about 30 seconds. And today, a modern scanner completes a full rotation in under 100 milliseconds. I mean, that is a truly mind-boggling leap in speed. So how did they do it? How did they get that fast? Well, let's look at this table. The key was changing the scanner's physical geometry. First-gen scanners, they used a single, slow pencil beam that had to move across, stop, then rotate. Really slow. Third-gen scanners brought in a wide fan beam that could capture a whole projection at once, so it only needed to rotate. And then,
helical scanners took that fan beam and moved the patient smoothly through it, capturing an entire 3D volume of data in one continuous motion. But of course, in the real world, things are never quite that simple. Getting that perfect image isn't just about being fast, it's a constant balancing act. You're always dealing with image quality, unwanted graininess or noise, and these visual imperfections that we call artifacts. And right here is the most fundamental trade-off in all of CT imaging: radiation dose versus image quality. It's pretty straightforward. A higher X-ray dose means more photons hit the detector, which gives you a clearer, less grainy image. A lower dose is obviously safer for the patient, but the image gets noisier. Every single scan is a careful judgment call. For a small child, the top priority is the lowest possible dose. But for diagnosing a really complex condition in an adult, you might need that extra clarity. It's a critical balance between safety and diagnostic accuracy. And even when you get the dose perfect, the real world can still interfere. Things like streak artifacts from a metal hip replacement can totally obscure nearby tissue. A halo effect around bone can sometimes look like a medical condition it isn't. And motion blur from something as simple as the patient taking a breath. That could be the difference between a clear diagnosis and an uncertain one. Overcoming these artifacts is a huge part of the skill of being a radiologist. You know, for decades, that filtered back projection algorithm we talked about has been the undisputed king of CT. But as our source material points out, things are changing, and they're changing fast. New methods called iterative reconstruction are now taking over. And why? Because they can produce images that are just as good, or sometimes even better, but with a substantially lower radiation dose for the patient. Which leaves us with a final and pretty fascinating question. As these incredibly powerful new algorithms get even smarter and even faster, are we heading towards a future of medical imaging where we can get perfectly clear, real-time images of our insides with almost no radiation dose at all?